So again, welcome to our Manufacture Anything webinar from Velo 3D. Today we're going to be talking about how support-free is enabling the next generation of metal 3D printing. But before we do, we're going to step back in time a little bit to the 1970s. A man named Garrett Brown invented a new way to film movies called the Steadicam. And at the time, there were a number of shots that were just known to be impossible. So in order to advertise his product, the Steadicam, he put together a video of 30 impossible shots and sent it around to producers and directors all over Hollywood. Stanley Kubrick was quoted as saying that this would revolutionize the way that films are shot. It's proved to be true. In 1976, one of the first movies featuring the Steadicam was Rocky. And if you remember the 72 steps that Rocky runs up in front of the Philadelphia Museum of Art, he raises his arms above his head in triumph. This was a triumph both for Rocky and for the Steadicam. So Garrett Brown filming impossible shots and revolutionizing the way that the industry worked. And you're going to see as we go through this presentation how that story is going to have an effect on 3D printing. So we're going to talk about manufacturing anything. Our first speaker is John Barnes from the Barnes Group Advisors. He's the founder and managing director of the Barnes Group Advisors. He has over 25 years in product development in aerospace, and his team has been involved in implementing additive manufacturing in aerospace and medical industries. He is a recognized contributor to additive manufacturing, product development, and leadership and engineering, and you can reach him at john@thebarnesgroup. John at thebarnes.group. Don't make the mistake I did when you type in that email address. Make sure you have the .group on there. John, I will turn the presentation over to you.
Great, thank you. Good day, everybody. So my team, we have a kind of a construct of how we like to help people understand and view additive manufacturing. We kind of look at it as four lenses, if you will. So we have machines, and I think this is, obviously pretty apparent. The machines are critical to the act of 3D printing, but it includes not only the printers, but some of the ancillary equipment that are necessary to make it happen. If we think about things as parts and not just prints, it requires the whole process to be taken into account. And so we see that space, it evolves, it's evolving quickly. We see more suppliers every year, and there's more models that suppliers are making. So the machines are getting bigger, which helps with the productivity, and that helps push the whole industry forward, which is overwhelmingly positive. The digital side sometimes gets overlooked because it's a fairly diverse crowd. It covers everything from the tools to do generative design, which is an enabler for technologies like additive manufacturing. It covers the CAD solutions, and that's also something that's getting better every day. It's making the job easier for the design engineer or the structures engineer to stay in a CAD environment. We're progressing past the STL file, and I think most people who are working with STL files are secretly or not so secretly very happy about that. There's a few engineers out there rejoicing quietly right now. We see there's methods for encrypting build files, and so when we put all this time and effort into engineering our build file, we want to see that protected. It also then comes across as a quality assurance measure. MES systems are out there now to improve the factory productivity, which helps the industry move forward. We evolve to capturing a lot of data that are existing in the machines themselves. And so we're now kind of getting to a point where we'll have more visibility to a part being made now than we ever have before in terms of quality, perhaps chemistry, perhaps defects or lack thereof. So that's an area of intense interest, and that's a very promising area of development. But also we're able now to simulate processes that we haven't, and that gives engineers a really great insight. And this is something that has preceded most of the manufacturing technologies before additive. You've always been able to get some simulation of an event, whether it be casting or forging, and that really gives you much better insight to design the part and design it to be made right the first time. So that's a positive development as well. But it's kind of the integration that becomes really interesting. You kind of have to get the machine and the software to come together. The simulation has to be synced well with materials data that's out there. Then the material and the machine can kind of be synced together. And what this kind of culminates, if you're doing it really well and you keep improving this synchronization or integration, is you're going to end up with higher productivity. And in a lot of ways, this translates into being smart with your support structure, and which, you know, if you're smart with your support, or you can eliminate support, you know, that hits all three cost areas for you. You use less material, you have less print time, and then you have less supports to remove when you're finished. So we see those as being overwhelmingly interesting areas to be involved with. And, you know, and of course, we love to talk about materials. Materials is coming on strong. You know, I'm a materials engineer, so naturally, you know, the materials people look at this field with big eyes, because we can see that there's a whole materials revolution waiting to happen, which, you know, is still happening on the plastic side, which preceded metals. And then there's the people component, and this comes to education and training. How do we get the existing fleet of engineers that are out there in the working world to think about additive kind of correctly and in the right context? It's not a solution for everything. It is a solution for some things. And so it should be part of that manufacturing arsenal that you have to bring to bear. Okay, Michael, I cannot, there we go. So we talk about additive and as a team sport. It's a very integrated capability. And if you look at a microcosm of that, just inside any type of powder bed fusion device that's out there, you'll see some combination of physics in terms of the optics, you know, whether you've got a laser or electron beam. You've got an environment, you've got a gas that's going on inside. You've got mechanics of materials as you are building parts. You've got support structure. You've got dynamics going on as you're heating and cooling and doing that repetitively. Then there's the metallurgy and material science that have to be matched with all of this to make it happen. If the materials aren't compatible, then you're not going to end up with a suitable product. And then there's a lot of the big data that's generated. There's a lot of analysis that goes on, and there's the simulation of these sometimes that we do beforehand. So this is a function of many things. And then we've got powder manufacturers flow and spreadability, and that is you know, distinct from material science, because this is basically how you get the material in there. How you produce the powder does matter. And things like how it's going to interact with the recoater blade. How is it going to get into place? How does it get moved around once it's in the bed? You know, the laser interaction with the powder is critically important. So we know we have to melt material. That's critical. Every degree above the melting temperature adds to distortion and residual stress, potentially. You can also affect your chemistry if you've got high vapor pressure elements. Chemistry can also be affected by the gas pressure and dynamics. So this isn't, you know, this isn't an easy solution. I think the solutions that we have today are really modern marvels in a lot of respects. So I think people, myself included, you know, may give the equipment manufacturers a hard time, but it really is a pretty incredible device when you really take a step back and look at it. So when we talk to people and companies about additive, you know, we try to express that this isn't simply a different end effector for a milling machine. Recently, we're at one customer, and he described it as this is bringing CGI to how to do animation for movies, and you know how you just don't show up and make a really advanced movie there. You similarly. I'm a runner, so you don't just buy a pair of running shoes and try to go run a marathon. If you're a pilot, you know, you don't go to work for Delta on the first day. You started with a single engine prop. So the way to think about this chart is that we kind of look at it as the products in gray, so that represents requirements, and then we've got learning and training in blue, and then you've got the levels. And so on the lower left, that's your domain of prototypes. And then on the upper right, you know, those are additively enabled products that can't be made really any other way. And so the industry necessarily starts down in the lower left. It's about making prototypes. It's a good spot. It does a lot of positive things for you. It reduces your costs. It improves your health and safety, potentially with shop aids and fixtures. It helps repetitive motions and repeatability for other operations. Then you move into that production influence. It's not making the part, it's making the tool that makes the part. This has been a really good area for 3D printing to come in, specifically with the casting industry. And then we got level 2, and now you're in production. So your product requirements have really come up. You're worried about your supply chain. You're worried about how your strength, is it anisotropic? So you need things like, how am I going to inspect this part? What are my materials properties? Do I have specifications? What's my business case? What are the process economics? You're starting to get some fluency in design for additive. And then that really helps you get to level 3, which is this part count reduction area. So you look at the neighboring parts and you're saying, well, I can take advantage of complexity with additive manufacturing. So we're starting to integrate parts. We're reducing, I'll say, structural inefficiencies potentially. If you've got brazing operations, fastening, welding, those things are sometimes less than parent metal properties. So that's a plus. That allows you to get to a lighter weight design potentially. But you're necessarily more fluent in design for additive manufacturing. You really have to be at this level. And on the top level, this is, you've got multiple functionalities happening. These are very advanced features. Maybe it's integrated cooling, maybe it's osteo-integrated surfaces. So these really can only be made with additive. And so at this point, you have to have that fluency in additive manufacturing, and now your supply chain reflects it. So, the way we always tell people is it's great to want to be in the upper right-hand corner. It's fantastic to stay in the lower left-hand corner. It's really a question of what your product requirements are. We're just simply giving people an ability to match what they have to do with the kind of learning and data that they need to get there. So Velo came to us and they said, how do we get faster growth in additive? And what does the industry really want? And so we took this and digested it and said, well, number one comment that we often get is education and training. And this is simply, people still, there's a very small community that understands additive really well. That community struggles, and I would put myself in there because this technology advances every day. There's new products, there's new machines, there's new processes, there's new materials coming out nearly every week. So it's very difficult to keep a pace on all of that. The training is important because it's about telling the engineers how to design for additive. What is it anyway? There's sometimes the push just to make it with additive when maybe there isn't a strong case to do that. You start with requirements and you figure out whether additive can meet those requirements. And if it does, great. So it's a different way of thinking about the problem for sure. It's a little bit counterintuitive for engineers like myself that have been in industry for a while. We're used to carving things out of rock. We've been doing that for many, 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 many years, going back to the Stone Age. But it comes into this design flexibility, and that has to have value to people. But in order to have design flexibility, you have to have really good understanding of what your requirements are. And so this is something that we teach in our classes every day. We tell the engineers, you start with your requirements, see what design flexibility that you have. And that's where tools like generative design come in, because they run through a rapid trade space for engineers to kind of give you an idea of what the structure ideally looks like. And then you need a human in the loop to say, well, yeah, but it's sitting in this environment, it needs to do something special. That's where the design flexibility comes in. And really the third part was manufacturing thinking. For additive to really get embraced by industry, it has to think about how the industry thinks about manufacturing things, and the industry needs to understand about how additive works. So this is very much a seesaw kind of operation. And manufacturing thinking is a lot of things. It is being very robust. It's being very reproducible. It's very consistent. And this is an area that additive has struggled with in the past. as do all new technologies. So very exciting. It's moving forward, and that's a testament to the technology. Robustness and quality, you know, I don't think that this bears too much comment. I think we all understand that this is something that a manufacturing device has to do. And productivity, you know, often is cost. It's about being able to print things, I'll say quickly, but efficiently. So we're looking at your dollar per hour on the machine. So productivity kind of disguises cost, because you can have a faster machine, but it might be more expensive. So you have to increase the speed without increasing the cost at the same rate. And that's where you get productivity. So when I started talking to Velo, what really was interesting to me was this support-free concept that they have. And it really hits on some areas that I think we've been waiting for. It's about that integration of the software, the machine, and the materials. And if you do that right, if you control the residual stress and the distortion of the material while it's heating up and cooling down and heating up and cooling down, you know, that allows you to reduce or eliminate support structure. And that is a big deal, because that's where you get into saving material, you get into saving print time, and you get into saving post-processing costs. So we've seen the polymers world, polymer additive manufacturing has taken this into account. They've come up with, if they still need support structures, there's been a lot of effort put into dissolvable, water dissolvable, soluble, or just eliminating support structures entirely. So it's a necessity for sure. Certain processes that are out there have gotten away with different ways of solving this problem. So in some of the systems that are out there today, you might have a heated chamber to 800–900 degrees Celsius, in which case that really drops your need for that support structure. And that's a different way of solving the problem. It also has some drawbacks in terms of pump down and heating up time, but it's been a great step in productivity. And if we look at the polymer world, you know, they're pushing down this path of less processing, less post-processing specifically, and that helps the cost picture as a part, more design flexibility, looking at how to do internal structures. The nesting density obviously helps your productivity. And this comes as a consequence of getting better adoption in industrial manufacturing. So in a lot of ways, we can look back at polymers and watch their progression, and we see metal following some of the very same models. So we see that now, you know, Velo has the support free, and, you know, again, this is very exciting for our team as engineers, because we think this is just positive for the industry. We think that this moves the ball forward for that upper right-hand corner of the maturity model area. And we believe that this will be very progressive for a lot of companies who've been trying to close a business case, but just haven't been. The flip side is, you know, it doesn't much matter to that lower left-hand corner. So this is about picking the right machine to do the job. That's how we look at the world. We're engineers, so we like to think that everything has a pro and a con. It's a balance. We're in equilibrium. You try to choose the right tool for the job. And but this is we see this as a tremendous benefit for pushing the field forward.
All right, thank you, John. It's my pleasure to introduce Tanya Jambazova. She's the Director of Product Management of Design here at Velo 3D. She has 2 decades of experience working at Autodesk in the digital design industry. She's also has a pretty good track record as a speaker, work at TEDx, so you can see one of her presentations on TEDx, and then numerous industry conferences as well. So Tanya, I will turn it over to you.
Thanks, Mike. Hello, everybody. And John, thank you so much for sharing your insights and experience, and for laying out the challenges as well as the opportunities of additive manufacturing. Additive manufacturing is indeed quite fascinating. It's exciting, and it's a true game changer for manufacturing. And we are already witnessing the polymer additive world is already moving from prototyping and tooling towards final production with additive. But the metal additive is still a little bit behind. It's still not yet fully there to be recognized as a reliable, reproducible production quality manufacturing method. So why is that? And John mentioned already, metal processes are much more complex problems to solve. Metal powders can be explosive, reactive. Powders change characteristics in presence of oxygen. They need super high temperature to melt. Melt pools on their own are hard to predict and control. And then the whole cooling and heating results in plastic and elastic behaviors that can create failures and deformation opportunities around each corner of the process. You can really think about metal printing as a sophisticated form of welding. And you know from the traditional manufacturing that welding is really kind of the weak link. As a consequence to this complexity of the process, consistency, quality, dimensional accuracy is still not there. The idea to production cycle still takes too long. And the much hoped for, but the limited design freedom is still an unsolved problem. These were the very facts what motivated Benny Buehler, the founder of Velo 3D. So in 2014, he understood where metal additive is, what metal additive can potentially solve, and he really wanted to tackle these issues. So he started Velo not in order to make yet another metal additive company, but rather to start addressing the root causes to these unsolved issues and limitations that hold back the whole industry and metal additive from becoming the production quality recognized manufacturing method. So what he had in mind is to approach the problem by building a system around tightly controlled process and failure prediction at every step of the process. And soon he realized that the only right way to do this was not to build yet another machine, but rather to build an integrated system of a process, hardware, and software in which the process is so tightly measured and controlled that we know the outcome is always what the designer designed, so that we can truly make the impossible. So there are many, many innovations within the hardware. We have worked on a unique to powder bed fusion closed loop melt pool control. And then we have sophisticated process-aware simulation-driven software, which in combination with the process and the hardware really creates a solution that enables users to make anything, but at the same time assuring that missing quality and consistency of metal additive. So we managed to introduce our breakthrough technology called support-free. So before entering into what Velo does for support-free, let's take a look at what support-free is or what even supports are. So in the polymer world, supports usually mean just that. They are physical supports. They're simply trying to defy gravity by preventing parts from collapsing during printing. But the word supports in metal additive does not quite apply. In the world of metal, where we weld and then we have rapid solidification of melt pools that create a residual stress, supports serve two other purposes. One and most important, it anchors the part. It restrains the part and it keeps it from moving up, which is basically what happens with the thermal distortion. And then it also serves as a heat transfer so that the next layers of the print don't come on a melted lava or a molten, but the heat is transferred properly. So John mentioned also that when it comes to supports in the polymer world, there have been developed technologies and methods to deal with how to remove supports, which is a big part of the work, right? And they're dealing with sacrificial and dissolvable materials. And that works for polymers. In the metal world, that is some early research that will not be reality for a very long time. So temporary support structures that are physically attached to the metal parts are the inconvenient necessity of metal printing and are really a big problem because they not only require a lot of post-processing and machining operations to remove them, which adds time and cost, but most importantly, it limits the numbers of designs that you can actually make with the current systems. So let's take a look at the example on the left. This is a shrouded impeller. It's usually a full circle part, and it has a lot of interior channels the surfaces above which are much lower than 45 degrees. So if you try to print a part like this with current additive metal technologies, you would need interior supports for every of those surfaces in order to deal with the problems that I mentioned before. On the right side, you see what we at Velo can do. We eliminate completely the need for interior supports because we have a unique ability to print these low angles and overhangs below 5 degrees, as well as other things like large diameters and inner tubes that I will mention later. And this not only eliminates the need to print these supports and thus to eliminate the need for post-processing and cleaning, but also opens the world of new parts and of much more of opportunity to design and innovate. That is what we call support-free. Now, if that is support-free, what are the implications of support-free? Basically, we are going to look through 4 lenses, how support-free helps in acceleration of the development time, because we know that in manufacturing, it's all about shortening the development time. Additive manufacturing was started as a rapid prototyping, but how can we arrive to rapid manufacturing? The possible, I always joke that if you tell an engineer that something is impossible, they will prove you wrong. They will always find a solution. But manufacturing is not only to find a solution, but to find a solution at the right cost. So we will talk about how support-free can help with the cost. Innovative is really about eliminating constraints so that we can start reconsidering design, so we can make existing parts or new parts to be much more performing. And finally, ultimate is the future of AM, where we really prove that AM can be better for time, better for cost, better for performance. So let's take a look through examples of all 4 of these. This is a stator ring. This part is a part of a jet engine. So how is it made today? In the traditional manufacturing, it's quite a long multi-step process. You first take a block of steel, you machine the internal ring, the hub, then electromechanical machining for each blade, then you separately machine the outer ring, and then you weld them together. Sounds simple, but it's a multi-step, multi-iteration process, and it's mainly the reason for long development times, and it's very prone to long lead times, because if you think about welding and casting, that those have sometimes more than 6 months lead time. With current additive manufacturing systems, you would need to support all of those blades as shown in red color on the image. What this means is that you need to remove them afterwards. These are very often very hard to access and thus hard to remove. To at all arrive to a functional stator ring in this case, you would need to go through a lot of design, prep, print, post-process iterations. You won't succeed at the first time in order to arrive to the part that you need. So this results in long development time, in long time to production. So how do we do that? Well, if you see the second image, you can tell that we only really need supports at the bottom of those blades. And by the mere fact that we do not need internal supports with our system, we dramatically use less post-processing time, we dramatically cut off the development time, and we have a 90% first pass success for each part. So as you can see, when we talk about time to market, this is how we accelerate it with the support-free capability. The second one is about possible. We'll go through an example of the shrouded impeller that I already showed. So in traditional manufacturing, again, this is a complex multi-step process. You first use a multi-axis machine to machine the component, then E-beam to weld the shroud, and then you weld everything together before the final machining. So there are different lead times associated with each process, and again, this results in multi-step, complex, low-yield manufacturing. If you look at conventional additive manufacturing of systems that currently exist on the market, this part will simply not be possible to be made, because as you can see, this is a fully enclosed part, but inside they will have to end up with lots of supports, because all of those top surfaces are lower than, in this case, this is a 10-degree shrouded impeller. So this will be just a forest of metal supports inside the part that are so hard or clearly impossible to clean. The result, not only the long time, but costly production with the traditional manufacturing and with additive manufacturing simply impossible to make. And by the way, yes, so how does Velo do it? Obviously, again, as in the previous example, we do not need any internal supports, which dramatically puts the cost down. The yield is higher and it's possible and affordable to do it with AM. Now, you know, when I first showed a couple of my friends who are engineers some of this part, they're like, oh, but I can machine this, I can machine an impeller. The thing that we don't talk about is, number one, yes, you can machine it in the same material, but we're talking here about one machine, one process, much more predictable, much more efficient. But the other side of the problem is that current machines can deal with materials like stainless steel, like aluminum, etc. But when it comes to Inconel or titanium, and those are two materials that have specifications and characteristics that are highly needed today that other materials don't have, they are extremely difficult to machine. Inconel is very good, has very good strength under high temperature. It has very good corrosion resistance. It responds very good to low temperatures, like liquid oxygen channels, etc. On the other hand, titanium has a phenomenal strength to weight ratio. It's biocompatible. It has also high corrosion resistance, which is super important for the medical industry. It has also high elongations. So when you look at how do you make parts with these two materials and try to do them with traditional machines, this is extremely difficult. They very often break the machines, or you have to do everything so carefully and so slowly that at the end of the day, the time and the cost do not pay off. The third example was about innovative. And when we introduce new manufacturing methods, they should better promise possibilities for innovations in our products. And additive surely did that. The reality, however, is that due to the many constraints and limitations of the current additive systems, designers who are using additive today have kind of learned to live with those limitations. And they only design within that allowed space. But that is really underuse of the possibilities of AM. AM can do so much more. And it is needed to do more because our world has growing needs for new, better solutions, for better performing products. We need to use less material. We need to waste less energy and fuel to do better medicine, etc. We need innovation. So the example that I have on this slide is a regeneratively cooling rocket nozzle. And this design has been around for about 40 years, or this part. It worked well, but there are always opportunities for improvements for parts, right? So this part traditionally was made by basically brazing copper tubing, and which is a relatively long process. This now can be optimized, made with additive, and it's optimized based on the manufacturing capabilities of additive. So we're talking about using this new technology to create better performing parts. And there is a more interesting side of this where I'm, as a designer, very excited. There are new generation of design tools that are emerging on the market, be it you've heard them as generative design tools that use evolutionary algorithms and just like nature use the least material for the best performance, or topologically optimization tools. They're implicit modelers that allow engineers and designers to design in a new way with product performance and optimization in mind. And these solutions allow for scalable complexity. So this on the right side is a heat exchanger that we developed together with Topology, a fascinating startup that has topologically optimization tools. And we managed to manufacture this complex triply periodic minimal surface part by controlling the behavior of the flow of the fluids. So these types of designs, as John said, could never be produced with traditional manufacturing methods. They are uniquely enabled by additive manufacturing, and many are uniquely enabled by Velo. And by the way, this part was built successfully at the first try, which made us very proud. So the last part is about ultimate, about the vision of AM. And here I'm showing you this part that is, well, we have different names for it. It was a test part, but it's not only beautiful because it has these amazing filigrane thin metal threads and lattices on it. But the more interesting thing is that this part was printed with our free floating method of printing. Free floating meaning it was not anchored to the build plate. We have not sintered the cake underneath. It has no supports at all. And we could put about 400 of these within the entire build volume and print them all together without them touching to each other or supporting each other. This is truly unique to Vela. This is part of the vision of additive manufacturing, but basically the full vision is really, can we bring additive to the level where the cost, the time to market, part performance, and also this vision of put a digital file in the oven and take out a functioning part comes out. And just so you can imagine what this means, here is a video of us printing acetabular cap, a hip cap. It's usually what is the part for replacing, for hip replacement. And it has been done with a lattice structure on the surface for good osseointegration. As you could see on the video, maybe we can run it again. These cups were printed next to each other and on top of each other. And this is after printing, we just take them out and the parts are ready. There was no supports, no removals. Post-processing is minimal, which is just a general post-processing, but it's highly efficient process. So instead of maximum 12, which, for example, other systems would have been able to build at the same time, we could build over 400 of those. So that's what we can do. So how do we do it? If you have ever been trained in additive manufacturing or design for additive, you have probably been told many things about unsupported angles, unsupported overhangs, bridges, about minimum feature size, about maximum wall height, etc. For a technology that was supposed to enable us to unleash creativity, there are way too many constraints at the moment. So we at Vela tried to remove some of those constraints. So let's take a look at overhangs. So what this diagram shows are different samples of parts that are basically showing different angle of the parts. So we have 45, 30, 20, and 10. There is this magic number 45 in the additive industry. What it indicates that the current AM systems, metal systems for sure, cannot build any overhang of 45 or lower from the horizontal without supports. So why is that? The process starts to become unstable. There starts to be roughness on the down-facing surface that increases with the lowering of the angle. And the parts curl up and often will clash with traditional recoaters, which is yet another problem. So here is how we do it. This is our sample part. As you can see, not only we can do it without supports, but if you look at the faces, at the down faces of these samples, the surface is impeccable, and it does, in many cases, not require any post-processing. And very important, we do this with a standard powder. We do not create anything special, no special powders, no special dealings with the material. It's off-the-shelf powder. So that is about the overhangs, and here are just some sample parts that leverage that capability. This is a normal impeller where you would traditionally need to have supports between the blades, or this diamond designed heat exchanger that was printed as you see without any supports, internal or external. Here another example, this is a turbo impeller that is lightweighted. We know that the aerospace industry is measuring on buy-to-fly ratio. We need lightweighting for using less fuel, for using less, for our vehicles to be lighter. So that is one way to do it. In this case, not only the blades did not have the supports, but these lattice structures designed, again, with end topology are highly consistent. Yes, other additive systems can make lattices. That's not the problem. The problem is that they really need to be consistent, and that is usually a problem with other systems. The next technical challenge that we solved are large diameters. You will also have learned about the fact that if you have large inner diameter channels, well, you can print only until 8 to 10 millimeter diameter without supports. Everything else, you need supports, or I've seen strategies where engineers are required to redesign in a teardrop shape the interior cross-section of those diameters. We at Velo have managed to push the limit to 400 millimeters in diameter without supports, or even bigger, depending if the part allows to be oriented on the build plate. So here is a part that we recently printed. By the way, on the right side, we should have put a coin. This is a business card, just to give you a sense of how big this part is. But what's really important about this part is not only that it's printed 5 centimeters or 50 millimeters without supports, but that the bottom skin of this upper part of the surface is really impeccable and it does not require post-processing. Another problem that you will often hear about is the high aspect ratio. Why is this a problem? Well, different systems have different recoaters. They can be hard recoaters that are like blades, or soft recoaters that are like windshield wipers. There are also roller recoaters. Regardless which, what they do is they are like bulldozers pushing powder on the print bed. And what happens is when you print a long and thin high aspect ratio object, they can clash with this object and thus move the object, and then obviously the build fails, but very often the recoater itself would also need to be replaced. At Velo, we invented non-contact or contactless recoater to avoid these failures, and also not to have to worry about, oh, you have to orient a part never to be parallel to the recoater because that's the only way in which it won't fail. Here is an example. This is also a heat exchanger that inevitably, due to the design, will have at least 2 fins that are parallel to the recoater, and only due to our non-contact recoater, we remove the potential for damage and are able to print high quality parts that look like this. And by the way, I heard that in the industry, the aspect ratio that is possible today is somewhere around 40:1. Don't quote me because I'm not sure if it's correct. We definitely can say that we can do 500:1 ratio. So that's what we can do. And how we can do it, as said, is by creating a very integrated system of process, software, and hardware. The software is not an afterthought. It has been designed with by being process aware, with the input from the process, and then it's driving the hardware that then delivers the value propositions that we showed. A few words about the software and the hardware. The hardware, we call it Sapphire. It's a powder bed fusion. It has a 315 millimeter diameter and 400 millimeter height build envelope. It has dual 1 kilowatt each laser. The contactless recoater and our own controllers are just some of the innovations. There is much more to talk about, probably in another webinar. But most importantly, the entire system has sensors, is sensorized, that we have integrated in situ process metrology that then allows us to have a true closed loop melt pool control, and thus know what is coming to the printer, and if it is not what's expected, the printer can self-correct on the fly or stop if there is an issue, or deal with the issue. That's why our failure prediction and risk in general for failure is very low. The entire system, as said, is built for volume production, and we tried to really marry the best concepts of powder bed fusion and EBM, which is around precision, about surface control, about dealing with multiple materials and high temperature processes. When it comes to the software, I'm happy to report that you're the first people in the world who are seeing this. We are actually launching our software next Tuesday. It's called Flow. And Flow is not just a print preparation software in terms of support generation and process overrides and smart selection, but it's really a technology bundle of 3 technological components. One is the print preparation environment, where you would be orienting the parts, supporting and applying supports and processes, and dealing in a very smart way, because we decided to break with the mesh workflows that are the industry standard, the STL file format, but decided to work on a native CAD workflow where you actually work with original SolidWorks, CATIA, name it files, or STEP and XT files. So this is something that we're very proud of, because it enables you to work in a much smarter way, and you can see a little bit of that in the video. The second part is the simulation aspect of this. We have built a simulation engine inside Velo, and this simulation engine helps both predict the print outcome, then apply deformation correction, knowing what that outcome would be, so that at the end we get the part that we wanted to get, and finally also helps with failure prediction throughout the entire process. Finally, Composer. Every printer has a slicing software. We call it a Composer because it's a much more sophisticated slicer that works on a multi-layer that is geometry specific and can apply the optimal process depending on the features. We also have a review of the slices that the Composer generates within the software. So let's take a look at the UI. I would have loved to make a live demo, but it's always a question of time. This is how the software looks like when you start. This is the dashboard. You import original CAD file. We do not convert it to a mesh. You're dealing with actual smart CAD. Here is an angle overlay that is often a good strategy for thinking how to select surfaces for supports. Here is a smart selection. What did I mean by smart when I said it's smart to work with CAD files? Well, let's say I would like to use to select all the blades on this stator ring. All I need to do is select the patch mode and select one of the blades, and then just ask the system to find everything similar. Here it is. This usually takes hours to make in other software. Then we introduce the concept of regions to organize the work. They are saved selections that help me then apply supports or apply processes. So here we are, we applied supports. Let's inspect with the section mode to see where all these supports arrived. Well, there is a forest of supports that actually Velo doesn't need here. So we will just reassign where the supports are needed. In this case, we'll just tell 10 degrees or 15 degrees or 0 degrees, whatever, and the system immediately updates. This was not sped up. This is how fast the software actually is. Then we can use the same method of regions to apply processes. I feel very strongly about this. We have an amazing process group, and we decided not to ask our customers to be the research lab people who are then failing and trying and testing until they arrive to success. We are doing the testing, we're doing the failing, and we provide you with processes that you can easily apply to the whole part or override per surface. The second part of the software is the simulation aspect. You are not going to see the simulation part of the software anywhere. It runs in the background, but this is what it does. It predicts how a part will deform. The part usually curls up. Then it applies this counter correction, counter deformation to the part. And then when we send these two parts to the printer, the left one was not applied to deformation correction, the right one was. After cooling, the right one shows correct and the left one will be curled up. We are very proud of this simulation engine and object print correction utility because, as you can see on the examples, it really helps arrive to the quality and dimensional accuracy that is required. And the last part, the Composer, also works in the background during the part preparation, but it allows you also, after the part is sliced, to review a bit the processes that have been applied layer by layer, not only in 2D mode, but also in the context of the 3D part. You can also look at the laser assignment or the print order and see if you got what you needed. Here is the printed part. We covered this before, and here really without explaining them, the 4 value propositions that you get with support free and Velo. Thanks, Mike.
All right. Thank you, Tanya. Real quick, we're going to go into Q&A in a minute. And so you can go ahead and start entering your questions now if you want to. We'll queue those up. I do want to preface that before we get to the Q&A, a little bit of our capabilities, and you'll see why in a minute. These are some of the industries that Velo's had success in solving customer problems. So aviation, space, energy, industrial, medical. We've talked about the metals. The Sapphire is capable of printing in titanium or Inconel. So it's Ti 64, Inconel 718. Those are the 2 metals that we have available. So if you're interested in those industries, if you're interested in those metals and specifically high value parts, and that's where we're able to solve the customer's problems the most. And you can kind of see some examples in the right-hand section here. The reason why I bring that up is we want to invite you to what we call the Impossible Part Workshop. So this is a workshop put on by both Velo 3D and the Barnes Group advisors. So the 2 of us are going to be working together in order to basically educate on what Velo can do for you and giving you a new design book. So the idea is if you have parts that look like they would fit on that previous slide and you've had trouble manufacturing them, we're trying to find a streamlined manufacturing solution, bring them to us and let us prove what we can do. Sign your company up for a session. The workshop has a value of $5,000. We are doing a promotion as a part of this webinar. There's a discount code field. If you enter support free into the discount code field, we can give you a 50% off. So it would be a $2,500 price tag for this workshop. It's about the same price as you'd pay for a single person going to a conference nowadays. So it's in-depth, multiple sessions with both the consulting group and with Velo engineers and experts. So it's very high value opportunity. We will be sending a flyer out and a registration link out after this webinar is over. If you have any questions on it or you don't get that link, just send an email to training@velo3d.com and we will be able to answer any of your questions. So that's the Impossible Part Workshop. Definitely take an opportunity to look at that. Thank you, John, and thank you, Tanya. Thank you, Greg, for awesome presentations and Q&A.
Thank you.
Please reach out to us at any time. The training or the info at velo3d.com is a great way to do that. And bring your parts to us. The Impossible Part Workshop, it's a resource. It's there for you to make sure that you feel comfortable that we can do what we say. So leverage it. All right, thank you very much. And you guys have a great weekend.
Thank you for your time, everybody.